So and then you can start.
Oh, I forgot to put a title page for this one. Okay, so today I'll talk about curvature and two types of curvature, or two notions of curvature. Those are the curvature tensor, that is the most complicated curvature tensor that there is. And then I'll talk about sectional curvature, that is the object that Riemann was looking to define when he began doing all of this, developing all of these ideas, and that in a certain sense is simpler than the tensor curvature, but actually the sectional curvature completely determines the tensor curvature. But okay, so in Rn, the Levi-Civita connection is given simply by differentiating a vector in the direction of another vector, which makes perfect sense since this was exactly what we were looking to generalize originally. And in this case, it is easy to prove that this identity holds. And this identity can be seen to be equivalent to saying that parallel vector fields, I mean that you can extend you take a point and you take a vector, and then that you can extend that thanks to this in Rn, you can extend that vector parallelly throughout an open set. Normally, you can only do that through along a curve, but in Rn, you can do that in a whole open set. So
just one question, and by this, do you mean that once it's defined in the whole open set, then for any curve you take, the associated vector field along the curve is parallel?
Yeah, exactly.
Yeah. Okay.
And then we can choose to look at this difference and interpret it as a measure of how far a space is from locally looking like Euclidean space, since this is a local thing, and also as measuring how far a space is from having the property of being able to extend any tangent vector to a parallel vector field. And yeah, and here there is a choice of sign, right? We decide to keep this as it is and pass this term to the side. Some people do things the other way around, and that changes some formulas, but I'm not sure which formulas are changed by that. The Carmo uses the other convention. Lee's book uses this convention. I mean, the convention that I used. So yeah, it is a little bit arbitrary. But one should be aware of that, because obviously the formula, I mean, at some point I'll express the components of this thing, because this is a tensor actually. in terms of the Christoffel symbols, and that formula does depend on which choice of sign we use. Okay, now the map defined by this difference is multilinear over C infinity, and then there is a result that says that if a map is multilinear, I mean, if a map of this type is multilinear over C infinity, then it defines a 1-3 tensor field on M. Yeah.
So question. So the I guess that the 3 comes from the 3 factors in the domain, and then the 1 comes from some adjunction formula that allows you to pass the codomain to the domain as the dual, right?
Yeah, but yeah, that's the point. Okay. But I mean, but there is no, in principle, there is no canonical way of doing that. Okay. I think you in Riemannian geometry you can canonically interpret 1-3 tensors of this type as 0 for tensors via the metric, right?
I see. Okay. Mm-hmm. So somehow you pass the codomain to the left, kind of using the isomorphism between the tangent bundle and the cotangent bundle provided by the metric.
Yeah, I think that's the idea. Actually, I'll do that later, because normally one doesn't use this, but you do what one calls lowering an index. I'll talk about this in a moment.
Okay.
But okay, since this is a tensor field, then it is determined in local coordinates by coefficients or components coming from the following equation, right? We evaluate the tensor. Yeah, maybe I should mention, some people call this the curvature endomorphism. So in that way, the 0 for tensor that it induces is the Riemann curvature or the Riemann curvature tensor. And some people call both of them Riemann curvature tensor. Okay. Now you evaluate the tensor in 3 local vectors from local coordinate vectors, ijk, and then you obtain their image in terms of the local coordinates, or the local basis, and the component belonging to the L coordinate vector is the component ijkl. So that's what this symbolizes. And one can calculate the coefficients in terms of the Christoffel symbols, right? So yeah, one fixes a Riemannian manifold, and in terms of any smooth local coordinates, the components of the curvature tensor are given by this formula. So yeah, the proof is simple. One simply takes 3 local coordinate vectors and evaluates them in the curvature tensor, and one obtains this first, right? One does not have a bracket term because curvature, coordinate vectors evaluated in the Lie bracket of coordinate vectors is always 0. Okay, and then one expands what is inside here and here in terms of the crystal field symbols. Then one uses the Leibniz rule to apply this part to this part and this part to this part. One obtains this. Then I put together what has crystal field symbols and what doesn't have crystal field symbols, right? No, sorry, yeah, of course. Here, I obtain once again the connection evaluated in a pair of coordinate vector fields, right? Here and here. Then I expand that in terms of the crystal field symbols, and then I'll obtain two terms that have a double sum. I put those terms together, and I put the other terms that are only a sum indexed by m apart. And then, yeah, we change the dummy indexes in the second term. We change the m for L. Where we have m, we put L, and where we had m, we put L, and where we had L, we put m. So as to have everything in terms of the same coordinate vectors, right? And then we look at the coefficient corresponding to a fixed S. And it will be simply this one, putting an S here, and the sum over S fixing M, right? Putting S here. And this is exactly what we want. Now, what changes is that if we look at the, if we had chosen the other sign for the curvature, then this, we would have to multiply this formula by -1, and that would be the difference, or one of the differences. Okay. Now, a classical result in Riemannian geometry is the Diviance identity.
So just, sorry, before you keep going, is it possible to give some geometric meaning or like an intuition to the definition of the tensor? I mean, of R of x, y of z. Like, is there like some way of knowing what it means geometrically?
Yeah, the closest to a geometrical interpretation I have seen is saying I want to extend a parallel vector field, a vector parallelly to an open set, and then one sees that difference is what that if that difference was 0, then one would be able to do so. But something more geometric than that, I don't think there is, because normally, at least in every book, they tell you this is a very technical object. For a geometric interpretation, one has to define sectional curvature. Yeah, so I don't know if that answers your question.
Okay, all right. Yeah, I mean, at least partially. Yeah, thanks.
Yeah, so the Bianchi identity that will prove, and for the proof, we should remember the Jacobi identity for vector fields. That's this. Okay. And this one, sorry. Yeah, I was talking about this formula yesterday and about its interpretation. And it does seem to have an interpretation, but I do not arrive to understand like the intuition behind it. But anyway. Okay, so by the symmetry of the connection, we have the following identities. We simply write this term first. It is this. We write this term here, and we write this term here. So let's recall that the symmetry allows us to express a difference like this one as the Lie bracket of y and z. So we first notice that we can express, we can put together this one and this one and obtain this difference by linearity. Then we can put together this one and where's the other one? And this one. Yeah, and obtain this. And we can put together this one and this one to obtain this third term here. And we leave the terms where we are differentiating in the direction of the bracket as they are. Then we use the symmetry of the connection to express this as a Lie bracket, as the Lie bracket of y and z, this as the Lie bracket of z and x, and this as the Lie bracket of x and y. And we arrive at this. And then here, we simply notice that we can put terms together again. I mean, this one with this one, this one with this one, and this one with this one. And by symmetry, their difference is simply the Lie bracket of, for example, in this case, it would be the Lie bracket of x and the Lie bracket of y and z. And in this case, it would be the Lie bracket of y and the Lie bracket, the Lie bracket of y and the Lie bracket of z and x, and the Lie bracket of the Lie bracket of z and x, similarly here. So we arrive at this, and this is precisely the Jacobi identity. So this is 0, and that's what we wish to prove. So yeah, I mean, behind all this idea of curvature, there seems the Lie derivative always seems to be like lurking around, right? We always try to compare our connections with the Lie derivative, which is not a connection, but is interesting in its own right. Okay. So as I said, via the metric, one can see the 1-3 tensor field or the 1-3 curvature tensor field as a 0-4 curvature tensor field, simply defining it this way, right? We take 4 vector fields and we evaluate them. The first 3, we evaluate them in the curvature tensor, and then we evaluate the metric in this curvature tensor, and the last vector field that we had. And well, one normally denotes the components of a 0-4 tensor field like this. We still put an R. We simply put all the indexes in them. I mean, down instead of 3 down and 1 up. And this is the reason for which one calls doing this. I mean, you can do this with an arbitrary 1-3 tensor field, and one calls this idea lowering an index, right? And these coefficients are determined by the following, right? We evaluate in four local coordinate vector fields. We use the linearity of the metric. Yeah, I mean, we say that we use that the tensor field evaluated in IJK looks like this. Then we use the bilinearity of the metric. And yeah, these are simply the definition, the components of the metric. And then we obtain this sum, right? Where we can express these things in terms of the Christoffel symbols. But the formula is to, I don't know, it doesn't tell us, it does not tell us much more to substitute the other formula here. So I prefer to leave it like this. So now this tensor has some symmetry properties that once again are, I find it really difficult to express them or to deduce them in a geometrical way. They seem to be very, very arbitrary to me. But yeah, I'll talk about that in a moment. So first, let's prove them, right? So we have these four symmetry properties. The first one is just the Diviance identity once again. Yeah, the second one tells us that we can permute the first two vector fields, and if we do so, we obtain a minus sign. The third one tells us that if we permute the third and fourth vector fields, then the same happens. And the fourth tells us that if we exchange the first pair of vector fields and the second pair of vector fields, then nothing happens. So yeah, as I said, the first one is just the identity once again. And for the second one, recall that the Lie bracket is anti-commutative, right? So the Lie bracket of x and y is exactly the same as minus the Lie bracket of y and x. Then by the properties of the connection, we have the following. We do this, we simply evaluate it as this is defined. Then we multiply all of this by a -1, which, I mean, we factor a -1 as -1 times -1, and we take by, yeah, in the first entry, right? And by bilinearity, we can take one of the -1s, and then multiply everything else by -1, right? So we change the sign of this and this, so they appear in the other order. And here, instead of changing the sign, we put the -1 here, right? So the sign stayed the same, but this term changed a little bit. Then we use the anti-commutativity, and we arrive at this, and that's exactly the curvature or the Riemann tensor evaluated in yx zeta. Now the third identity.
Just 1 second. Isn't there a minus sign missing?
Yeah, here. Yeah. Sorry. Here there is a minus sign missing here.
Okay.
This minus sign I didn't put it. Yeah. Then the third identity is equivalent to proving that for 3 arbitrary vector fields, this is always 0. So we consider the following. We simply write this by definition. And then we notice that this term is part of applying y to this function, right? And that can be expressed by the compatibility of the connection as the sum of this term and this term. Then this term is the difference between this and this. And we can also do the same with this other term here. And for the third term, we notice that it is, once again, here I have a parenthesis, one parenthesis more than I should have. But yeah, this term without the minus sign is the same as 1/2 of letting the bracket act at this function. Yeah, this is similar to the way that one does the same when thinking about the usual inner product, or one can do the same. And then we simply substitute. Yeah, we would substitute this term by a difference and this other term by a difference. Both of them have this term here, one with a minus sign and the other with a plus sign because of this sign. So this one goes away, and we are left with only this type of term here and here, and this is the other term that we had. And then we notice that this term can be interpreted the same way, or we can deal with this term the same way we dealt with this term, right? So this term can be seen as 1/2 of letting, y act at x acting at this function. And one interprets this part similarly. And then this, that we obtain 1/2 multiplying all of this thing. And this is precisely the Lie bracket of x and y acting at g evaluated at zeta, comma zeta.
But just wait. There is kind of a mistake in the signs, no? I mean, in the first and second rows.
No, there is no mistake. Sorry, this term is this one, and this term is this one. Yeah, no,
but still, no. I mean, I mean, in the very end, I think it's fine. It's just let's say in the first row, you know, the yg blah blah appears with a plus sign, and xg blah blah appears with a minus sign, and I think it should be the other way around.
Let's see.
Because if you look at the previous slide,
g x zeta, y x zeta, y x zeta.
Because in this slide, what you have in
of
the
course.
middle row,
this should be the other way around, right? These two. Yeah, that's that's a problem that I had because of the choice of sign that I made, because this proof I followed it from the Karma, and I forgot to change that. But yeah, these two should be the other way around. And here there's also a mistake here, right? Because here it should be xy of zeta and zeta, not x zeta.
Right.
So that they actually do eliminate. But yeah, that's right. These two should have different sign. And then to prove 4, we first apply the Diviance identity, and this is the one that I found most arbitrary as a proof. I do not think it is in any way intuitive, because actually we will not. Yeah, ideally what we would like to prove is that the curvature tensor evaluated at x, y, zeta, and t is the same as the curvature tensor evaluated at zeta, t, x, and y, but in the end we will not arrive exactly at that. We'll see in a moment. Okay, so we take these 4 versions of the Diviance identity and we add them up and use the other 2 formulas that we have to put terms together. So this term here, zeta x y t, goes with yeah, this one goes with this one, right? Because we can permute this one and this one, and we obtain a minus sign. We can permute this one and this one, and we obtain a minus sign. And so we have a positive sign, and then we change this pair and this pair. Or we can first change the pair and then permute 2 times. So this one and this one are the same, hence the 2. And similarly with this one and this one, right? No. Or yes. YT zeta x yeah, because this term should be the negative of this term, right? We have this. I can change this one and this one, but then I only change y and t and I obtain this term with a minus sign, right?
I'm a little lost. So you are trying to see how the cancellations go, right?
Yeah. Yeah, and yesterday when I thought about it, I thought that one could obtain, like, from this row all the things that don't cancel out. But
like for instance the last term, the third term in the first row, isn't it equal to the last term in the third row, the first and third row? So take the first and third row, the last terms, and then for instance take the first row in the third term in the first row, and then exchange x with z and t with y.
Oh, yeah, I see. Yeah, I see that. That's what I should have done. Yeah, this one and this one are the same, and this one and this one are the same. Yeah, because here I only exchange this one and this one, and this one and this one, and then I obtain a sign. And this one, I permute this one, and I permute this one, and I arrive at this with a positive sign. Yeah.
And then somehow the sum of all the first 2 terms should vanish somehow, right?
Yeah, and you simply look at a particular term and you see that it is the negative of another term. For example, x, y, zeta, t is the same as x.
Right, you go to the last
x, y,
row.
t, zeta, for example. This one and this one.
Yeah, right.
And yeah, you do the same with every single term.
Yeah, okay.
Yeah. And this is what we wanted to prove, right? Because one simply passes one of the terms to the other side. No. It is what we wanted to prove. No, if it was what we wanted to prove, this should be a negative sign, right? Because we want to pass
but
this.
it's fine, no? It's fine because you know the coefficient 2 cancels, and then when you pass one term to the other side, you have a minus.
Yeah.
No, exactly. yeah, you are right. Something strange. Yeah, you are right. Right. I mean, the thing is, yeah, it should be a minus sign, and it's because, for instance, look at the last term of the last row above, and it says yt xz. Mm-hmm. But what you have underneath is yt zx. So somehow, I think you are exchanging x and z. That's why that's where a minus sign should appear, no?
Yeah, here and in the other one. Yeah, here and here we do the same, right?
Right.
So the minus sign appears, and we pair this one with this one by doing.
Yeah. So in the last equality, the second term should have a minus sign. Yeah.
But yeah, okay. The second term should have a -1. If not, this does not make sense. But I think that then one cannot pair this one with this one because that would have a negative sign, right?
No, I mean the first one and the third one, you can pair them. It's okay because you permute z with x and y with t.
Oh yeah, you leave this one as it is and you permute it. Yeah.
Okay.
Yeah, I agree. Yeah, okay. So this should be a minus sign, and then we can cancel the 2 and pass 1 to the other side, and we have the equality we wanted, although not with the vector field we wanted, right? But because ideally this would have been x, y, zeta t, and instead of that it's zeta x, y t. But one can simply substitute by that one once. Yeah, that's the fourth identity that we wanted to prove. And now what this tells us is that we do not actually have to calculate all the Christoffel symbols, right? All the components of the curvature, because some of them are determined by the others. So the question of how many must one calculate is one that I don't know. But if I don't know if it is simple to give an exact number. But yeah, at least one knows that one does not have to calculate all the terms of the tensor, all the components of the tensor. Now, well, or imagining trying to calculate of all the components of the curvature tensor, one sees that it is a complicated problem. So we want to find a simpler notion of curvature. And that's sectional curvature. And that as I mentioned, this was the original idea that Riemann had. Okay, so he thought, because he was trying to generalize Gaussian curvature to a manifold that first of all was not embedded in R3, and second of all that it was not necessarily of dimension 2, right? So it was not a surface. So what he said is we can look at a point in the manifold and look at an arbitrary surface passing through that point, and at the tangent plane at that point, and then calculate, or look at that point and calculate the Gaussian curvature at that point, right? So for this, we will denote this difference here as the absolute value of the wedge of x and y, right? And we let sigma. So, and we want to prove, or we want to say how to calculate this thing that we'll call the sectional curvature. That is essentially the fixing a point. It is the Gaussian curvature of a surface that passes through that point. So we fix a two-dimensional subspace of the tangent space at P, and we let x and y be two linearly independent vectors. Here I'm missing an S. And then this formula here, or this function here, that does not depend on the choice that we made for a basis of sigma. So that we can define k of sigma as k of xy for any basis of sigma.
Yeah, just 1 second. So this what you are calling the absolute value of x wedge y. So each square. I mean,
why can?
So I guess you are really defining this kind of this sort of absolute value function as a function from the wedge of the tangent space with itself to the real numbers.
No, the wedge is not the wedge in the usual sense. This is just notation, right? This is supposed to denote the area of the parallelogram formed by these two vectors, right? Or spanned by these two vectors.
Okay.
Yeah, that's
okay.
Carlos, is it like supposed to like emulate the notation for an area element if we wrote instead of x and y like dx and dy or something like that?
Yeah, I think that might be the reason for when uses this notation. And something else. Yeah, this is not 0 or smaller than 0 because of the Cauchy-Schwarz inequality. Right? That's something important to notice, because if it was 0, this quotient would not make sense, and if the difference was smaller than 0, then the square root would not make sense. Okay. So for proving this, we observe that given a basis, we can pass to any other basis simply by iterating the following transformations that are these ones here. And then we observe that these transformations preserve the value of k. Yeah, this one is obvious that this one and this one obviously preserve the value, and this one is the only one that it's a little bit not tricky but difficult to prove. I mean, it's a rather lengthy calculation, but it is quite straightforward. So yeah, that's the idea. Then, given the previous proposition, we can define the sectional curvature at any point P for any given two-dimensional subspace of the tangent space at that point P, as this thing here, where x, y are simply the members of an arbitrary basis of C. And now, now I'll calculate. I'll pass to calculating the sectional curvature of the hyperbolic plane. But before that, I should mention that the sectional curvature and the curvature tensor are essentially the same thing, in the sense that one can go from here to, one can, from the curvature tensor, one can construct the sectional curvature, but the other way around is also possible. The curvature tensor associated to from a certain sectional curvature, we can construct or determine the curvature tensor completely. And then one can see that to calculate the curvature tensor to prove that the sectional curvature is constant, in the sense that at every point for any given subspace, it has the same value. It is enough to calculate it either to prove that the value depends only on the point and not on the subspace chosen at the tangent space at that point, and also that it is enough to calculate it at least in a local chart at the subspaces spanned by pairs of vector fields of local coordinate vector fields. Okay, but I decided not to put that here because since we are working in dimension 2, it is unnecessary to use those ideas. In dimension more than 2, it is necessary to use them, because calculating the sectional curvature of an arbitrary subspace is quite complicated. Okay. So now, we want to calculate the sectional curvature of the hyperbolic plane, and since it is a two-dimensional manifold, each tangent space has a unique two-dimensional subspace itself, and this simplifies the calculations considerably. Okay, to do our calculations, I decided to use the semi-plane model. And recall that the metric in that case is given by this coefficient here, right? Gij is simply delta of ij over x over the second variable squared, right? Yeah. Okay, so now, as I said, to calculate the sectional curvature in general is enough. It is enough to calculate the sectional curvature in terms of the basis given by the two coordinate vector fields that in this case are not defined only locally but globally, since we only have one chart. And so we want to calculate the Riemann curvature tensor evaluated at this, and the other thing we defined evaluated at the partial 1 and partial 2, right? And well, one can notice that this is equal to 1 over x squared to the 4. We can return here. Yeah, one doesn't have to look at the square root. Simply, this one will be 1 over x2 to the square. This one will be 1 to the x2 to the square. When we multiply them, we obtain 1 over x2 to the fourth, and this is 0 because the vectors will be different. Right? Okay. On the other hand, we have that this can be expressed like this, right? So we are trying to calculate the coefficient 1, 2, 1, 2 of the Riemann, of the 0,4 Riemann curvature tensor, and this one can be expressed as a sum of terms of the 1, 3 tensor field. That looks like this, but every one of these terms will be 0 because G, almost every single one of these terms will be 0 because G of L2 is 0 when L is different from 2, right? So we are left only with this term, and this term is G of 2, 2, so 1 over x squared to the 1 over x2 to the square, 1 over x2 square, and then we only have to calculate this component of the curvature tensor, right? So yeah, here we see that at least in principle the sectional curvature is simpler, because to know it, we only have to know one of the components of the curvature tensor, whereas to know the whole curvature tensor, we would have to calculate 2 to the 4 coefficients, right? At least in principle, without considering possible symmetries. Okay. Now, we now calculate the Christoffel symbols. We recall the formula that we proved yesterday. That is this one. Now here I'm missing the one of, okay, we have this, but once again, most of this term cancel because here G of G to the Km is the inverse of G Km, right? Yeah, I mean, denotes the entries of the inverse matrix. And this, since the metric is conformal, the inverse is very simple and is simply the identity matrix multiplied by the inverse of the function by which the metric is conformal, right? So it would be x2 to the squared times the identity matrix. And then that will tell us that these things cancel for almost every k except when k is equal to 1, right? So we only have here, it should say 1 over 2, this term here. And then then GMM is x squared to the 2, x2 to the x2 squared, sorry. And to calculate this, we simply notice that G of JK, we can calculate this and then substitute simply the indexes, right? Since we can see IJ.
Just one question. Why this, for instance, this GJK? I mean, isn't that 0 if J is different from K?
Yeah, exactly. It is 0, right? When J and K are different, but when J and K are not different, then it is not 0. Then it isn't 0.
Right.
So this thing.
I see. Okay. Yeah, I understand. Yeah. Okay.
Should be expressed in terms of the Kronecker deltas, no? Right. So first we have the Kronecker delta of J and K, but then also, since the function actually only depends on the second variable, then when this partial, the I is 1, the derivative will be 0, right? So then we also put a Kronecker delta of I and 2. And then we simply differentiate. We simply differentiate this in terms of x2, right? And we arrive at this. Yeah, I mean this with a negative sign that I already put here. And well, yeah, when one does exactly the same thing here and here, right? So in here we would obtain delta.
And it's really there where the denominator 2 disappears, right?
Yeah. Yeah, here I should also have the denominator 2. You're 1/2, right? Yeah, so here we'll have delta of j and 2, and here and times delta of k and a, and the derivative of the function. And here it would be delta of k and 2 times delta of I and j. Okay, now we can factor this thing here, and we are left with this square here. Here I missed the square, right? Because, oh no, sorry, it is correct. It is correct. Because this one is to the power of 2 and this one to the power of 3. So 2 of these cancel and we are left only with 1. And then from here, one actually knows all the Christoffel symbol, but there is no elegant way of doing it, right? One simply substitute this by the 8 possible arbitrary combinations, and once is this and once is this. Actually, originally I wanted to do the calculation as if we were working, as if we were trying to calculate the sectional curvature of the hyperbolic n space. But yeah, the part where you calculate the Christoffel symbols seems really horrible. Actually, it seems to be much more simpler to do, yeah, instead of using the explicit function, to do everything in terms of an arbitrary function, but then one doesn't have the explicit value of the Christoffel symbols. One simply arrives at an expression for the sectional curvature, and that is a much more handleable, easily to handle expression. But yeah, so these Christoffel symbols will be 0. Then these 3 other Christoffel symbols will be -1/x2, and the one that's left is 1/x2. And then we can now calculate the component of the Riemann tensor in terms of the Christoffel symbols, right? Here I just use the formula that I proved earlier. But actually I used Carmo's version of the formula because at some point I made the same choice of sign than Carmo makes. And I'm not sure if it has to do with the way I defined sectional curvature.
Just one second, sorry. In the previous slide, right? Shouldn't K be M?
Where?
It kind of from the second row to the last one. Shouldn't K be M? Because K was a summation index.
Yeah, here. Yeah, you're completely right. Here I should have M, 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 and
right.
2. Yeah, or I could have just put K here, right? And I mean, but I should have put K here actually. But yeah, there's a mistake.
Okay.
You're
okay.
Right.
Okay. Thank you.
Yeah, and here there is Yeah, here the formula is correct, right? Because I can say, oh, I changed the M by K, which is not very elegant, but at least the formula alone is correct. But yeah, it should say M instead of K. And well, okay, now one can calculate this. And then this first term will be 0 because, because this one is 0, right? Or is it the other one? Is gamma 1, 1, 2, 1. No, sorry, this term, this one is this one, right? So when we differentiate, we obtain -1 over x2 to the square from here. Then this term is 0 because the Christoffel symbol associated to the term is 0. It is this one here. And one can once again do the calculation and see that this whole thing will be 0. The term associated to m equal 1 will be -1, and the term associated, sorry, not -1, but -1 over x squared over 2 over x2 squared, and the second term will be 1, or the term associated to m equal 2 will be 1 over y over x squared. So those two cancel, and we are left only with this term that has this value, and hence not this component, but the component of the 0,4 tensor field has this value because we multiply by the other 1 over x2 to the square. So we obtain this, and then to calculate the sectional curvature, we simply divide this by this that we had calculated before, and that leaves us with a -1. And yeah, that's how to do that's how one does the calculation. Okay. And yeah, that's all that I have for today. I don't know if I might be able to say more things, but I don't know if you would like me to say something else.
Yeah, I mean, how long would it take you to? Like,
no,
I mean,
I'm done with what I had prepared.
Okay, all right, okay. So, okay, thank you. So I just have a question. So, you know, this pseudosphere or tractrix, right? Do you know, whether this pseudosphere or part of it can be seen as the isometric image of the hyperbolic plane inside R3?
Well,
you know, with in R3 you put the Euclidean Riemannian metric and all the restrictions you always take them to come from the Euclidean Riemannian metric, and now consider the hyperbolic plane kind of abstractly, if you will, as a Riemannian manifold. And then kind of my first question is it true that the pseudosphere or part of it, let's say a closed subset of it, can be seen, or open subset of it can be seen as an isometric image of the hyperbolic plane or of some open or closed subset?
Yeah, I think, I'm not sure if the whole pseudosphere can be seen as an isometric image of some subset of the whole of the hyperbolic plane, right? But thinking, let me just but thinking about the disk model, I think, well, yeah, first of all, it is at least intuitively clear that one cannot see the whole yeah, I would think it is clear that one cannot embed the whole disk as the sphere, right? Because, or the whole hyperbolic plane as the sphere, because their topologies are different. Yeah, the hyperbolic plane is simply connected, the pseudosphere isn't simply connected, right? Second, I don't, this is not intuitive, and I'm not sure if it's true, but I think that it is also impossible to embed a part of the hyperbolic plane as the whole pseudosphere, because once again, the pseudosphere seems like a cylinder. I'm not exactly sure if it's like a cylinder because of the infinity thing. But I do not see how to construct an object in the hyperbolic plane that has that exact same kind of topological property, right? Do you agree with me, or more or less, at least?
Yeah, I think so.
And the third part, I think that one thinks about something like this. In the hyperbolic disk, then one should be able to embed that. Okay, so the whole, I don't know, I'm very bad at drawing, but the whole pseudosphere is something like this, right? Where this simply goes to infinity. And I think that one could like take half of it and make it correspond to one of these kind of triangles. And that's, I think, the relation, so that they are locally isometric, but not isometric, obviously, because they have different topologies and so on.
Right. Yeah. So the thing is, my next question is, in that case, you know, you can then compute the curvature on the right hand side in the of the pseudosphere, kind of following, you know, just a basic course in differential geometry, right? Like kind of using this normal vector that now you have because it's embedded in R3 and so on, like in the Carmos book. My question is, if you do that, do you get? I guess you have to, right? Yeah. Yeah. But anyway, yeah. Do you get the same curvature -1?
Yeah, of course. Yeah. Yeah, it is possible to do that. I actually did it at some point of my life.
Right, and then somehow, what's the meaning in, you know, for surfaces in R3? What's the meaning of having curvature, let's say -1, let's say everywhere?
I think it is simpler to explain what it means to have curvature -1 at a point.
Okay.
And the idea here is that the curvature can be expressed in terms of these things that one calls principal directions. But I don't know, that's too complicated. But the idea is that one has some things that are called principal directions, okay, that are directions in which curves curve in a certain way, or in which curve the most. So when one has the plane, for example, every direction is principal, right? So we can simply take two, and I think I'm almost sure that all of them, the principal directions must be orthogonal, but I'm not completely sure about that. And then the idea here is that one can take the tangent plane at that point, and any curve yeah, maybe there is a little a more delicate problem. One can say that the curvature is positive or zero at a point if, when you take a look at the tangent plane, at that point, every curve stays in the same side of that plane, right? So yeah, I fix my tangent plane here, and all the curves that pass through that curve always stay over that tangent plane, right? They do not cross it. In the case of positive curvature, such as in the sphere, we have a similar phenomenon, right? One takes a point, one takes the tangent plane at that point, and at least locally, I mean, here it happens globally, but locally, any curve that you take will not cross the tangent plane. A negative curvature happens when at a certain point you have curves that cross the tangent plane and curves that do not cross the tangent plane. So, and I think the principal directions will fulfill this. I mean, a curve in the principal direction will cross the tangent plane, and a curve in the other principal direction will not cross the tangent plane. So that's the way of visualizing curvature in Rn. And one cannot say other. There are other ways of doing this. There's this paper by Gromov where he talks a lot about the meaning of curvature. It is something like what is the meaning of curvature or something like that. I do not remember the title. And he gives several criteria to distinguish the curvature of surfaces embedded in Rn. The problem is that when one doesn't look at something embedded in Rn, then the metric is not necessarily the one induced by Rn, and yeah, then one cannot do pictures, right? Because they do not necessarily represent what is happening. And yeah, in that case, the interpretations that one can do are mostly topological, right? For example, we know that if a manifold has negative curvature bounded away from zero, then that manifold must, its topology is completely determined by its fundamental group. So that its covering is always the hyperbolic disk. It's universal cover. That's a geometric interpretation, but it is not absolute, since the same idea for arbitrary curvature does not hold. I mean, you cannot simply say if the curvature is this, then the topology is determined by this. Yeah, I don't know.
Okay, thanks. But so that's the reason why many people draw like negative curvature as a point as a saddle.
Yeah, exactly. Saddles have negative curvatures because the one of the principal directions will be this one, and the other one will be this one. So when you look at the tangent plane, one crosses the tangent plane, and the other one crosses the tangent plane, and the other stays in the same side of the tangent plane.
Just one more thing. But couldn't it be rather said that that what happens is that in this kind of sort of saddle points, what happens is that for one principal direction, kind of you stay in one side, and for the other principal direction, you stay on the other side of the tangent plane, rather than crossing or not crossing.
Yeah, sorry, you're right. I'm sorry. You're completely right. What I said is wrong. Not that it crosses the tangent plane, but exactly that there are curves in one side and curves in the other side. Yeah, you're right. I was thinking incorrectly.
Okay. Well, thanks. Okay, so I'm going to stop the recording.